This slide is the backup chart showing the detailed block diagram of uniform voltage distribution controllers. Basically, the uniform voltage distribution controller converts the primary system control voltage VC into multiple control voltage VC1, VC2 and VC3 appropriate for controlling power converter number 1, number 2 and number 3 in such a way that the feedback voltage or the sourcing voltage or the input voltage across those converters V1, V2 and V3 are uniformly distributed or equal. Basically, the input voltage distribution controller shown in this block diagram compute the minor correction signal or voltage VD1, VD2 and VD3. This minor or small correction voltage we call it distribution error signal. Subtract this distribution error signal from the primary system control voltage, providing the distributed control voltage VC1, VC2, VC3. This slide also shows the detail of uniform voltage distribution controller, emphasizing the particular control approach called maximum limit distribution control. Basically, the ideal rectifier that select the maximum voltage candidate from the three sourcing voltage. The highest sourcing voltage is then served as the common reference VDIS. The common voltage reference VDIS provide a basis for each sourcing voltage to compare and generate the distributed error signal VD1, VD2 and VD3 through this voltage distribution error amplifier. In this manner, uniform voltage distribution controller able to generate the minor control corrections voltage signals VD1, VD2, VD3 and feed upstream to make a correction to the primary control voltage shown in the previous slide. This is another slide that shows the detail of maximum power tracking controller. Basically, the maximum power tracking processing circuit process two signals. One is the signal that represents power signal. In this case is I bus, which is the total sourcing current from the dipole converter, representing power signal. Another signal is called digital signal, which is the AC signal, representing AC ripple voltage across power sources. Since the power source already actively regulates to the digital signal, there is no need to feedback the sourcing voltage directly into the MPT control circuit. Digital signal is sufficient to provide the internal feedback together with the I bus that represent power signal. In these two parallel pairs of feedback called power signal path and another path is digital signal path, uniformly process the power like a bandpass filter in such a way that the high frequency noise is rejected and the extremely low frequency noise also eliminated, or the DC component of the signal already discarded. The maximum power tracking controller purely process the AC information with respect to the power and the sourcing voltage. Process together using the comparator to convert the analog into discrete signal, and this discrete signal process to exclusive or logic to generate the information with respect to the phase shift between the two signals, the power signal and the digital signal. The phase shift between these two signals is processed to the exclusive or logic that act like a phase comparator. When these two signals are in phase, which is usually happen when the power operating point is on the left side of the peak power, they are in phase. And when the peak power are on the right side of the peak power point, these two signals are out of phase. And when these two signals corresponding at the peak power point, these two signals are approximately have equivalent phase shift about 90 degrees. When that happens, or the peak power point is approaching, the output of the exclusive or logic will be at the middle of the power supply voltage. As a result, the integrator will stop integrating, or the set point voltage VSP will be steady or stay at the final value. So this is the way that the MPT controller works. The digital signal also add back to the voltage set point VSP, so that the voltage set point VSP also contain this low frequency digital signal, and the total set point voltage VSPT become the commander signal for the input voltage regulator, so that the system sourcing voltage can be controlled to track this set point voltage VSPT. Okay, this is another backup chart showing the signals around the MPT controller at different conditions. On the upper top left corner of the chart, showing the power signal in red color, and in blue color also showing the digital voltage. When both the power signal and the solar array or sourcing voltage ripple are in phase, this corresponding to the operating point when the operating peak power is on the left side of PV characteristic with respect to the peak power point. Now, going next to the lower left hand side corner of the chart, you can see that the power signal show on the red AC curve, and the voltage signal, which is the sourcing voltage signal or solar array voltage signal, on blue curve, revealing 180 degree phase shift or simply out of phase of each other. This corresponding to operating power is on the right side of peak power point. When this is plotted in the PV DC characteristic. And finally, on the right side of the chart, the top plot shows the instantaneous power signal, with showing the ripple that have a double frequency effect. This is the total sourcing power that extract from 3 power sources for this example, for the system of 3 power source. When the system deliver the output current ripple that show in the purple or red color, it show the phase shift about 90-degree phase shift with respect to the sourcing voltage in blue, signifying that the system already around the peak power point or at the peak point of the PV DC characteristic.